So now that we've begun talking about solutions, we're going to talk about another type of solution. It's called an electrolyte. I don't know what you're all thinking. Gatorade. Sure. We'll see what your opinion is on that after we're done. Electrolytes are solutions that conduct electricity, and this relies on ions being present in solution. Obviously, charged particles make sense. That's how charge gets from one place to another. Molar ratios, in molecular formulas will dictate the moles of ions in solution. When you dissolve a compound in water, you add water to a compound, and you predict how the species will act when dissolved. Pretty straightforward. Solid or pure liquid species on the reactant side, aqueous species on the product side, obviously aqueous meaning dissolved in water. So, word of the wise, we're going to start with a very simple example. You're going to see a trend with ionic compounds and molecular compounds, and we're just going to dive right in. So, when NaCl is dissolved in water, right? We make salt water. We've all done this before. It actually splits up into the ions that compose the NaCl solid. So when we dissolve those salt crystals into water, we have sodium ions floating around, and we have chloride ions floating around. And that's what the solution looks like. If you zoomed in really, really far, you have little Na pluses and Cl minuses floating around. But you wouldn't have anything floating around as one unit of NaCl. That is because sodium and chloride, right, when they're bonded together, sodium is positive, chloride is negative, so there's a little bit more electron density around the chloride in that sodium chloride compound. One for complex, not the right word. Sodium chloride compound. So we can say that this is a polar substance, and you'll learn more about polar, non-polar, all this fun stuff in chapters 8 and 9. But for your intents and purposes, there's a negative charge concentration at the chlorine, positive charge concentration, or just tendency to the positive charge concentration at the sodium. This is a polar substance. And water is a polar solvent, so polar substances are dissolved by polar solvents, the same way that nonpolar substances are dissolved by nonpolar solvents. Okay, so this makes the ionic compound break apart, right? And notice that the molar ratio is the exact same, right? So there's one sodium for one sodium, one chlorine to one chloride. And it really is chloride in this one. I just went with chlorine because there wasn't a charge on it. Another way that you can write these reactions is you can just start NaCl solid on the reactant side, longer arrow, just write H2O, showing that you're adding water, and then you can show the same products. Now, we can do this with a polyatomic anion as well, and we can do it with potassium dichromate. And just remember to identify potassium dichromate, right? We look at the two parts, so we have the positive side of potassium and the negative side of dichromate, right? So that Cr2O7, that in and of itself is a polyatomic anion. If you have not seen that before, now you've seen it, good for you. So we can do these reactions with potassium dichromate as well. So we can go K2, Cr2, O7, solid, nice long arrow, H2O over the top to show that I'm dissolving in water. And I get, and actually try and do the products yourself before I fill it in. So pause the video, see if you can figure out what this is going to be. So, completing this process, right, we get 2 moles of the potassium ion. So they don't float around as little K2s. Potassium ions are +1, so they float around individually. There's just 2 moles of potassium ions for every 1 mole of potassium dichromate that dissolves. And there is 1 mole of the dichromate anion for every 1 mole of potassium dichromate. So, these coefficients, right, and remember there's an understood 1 there, right, you have to, again, make sure your reaction is balanced. This goes back to that stuff. So, just making sure, checking, filling in all the lines, crossing your T's and dotting your I's. Wow. it is definitely a Monday. So we're going to go on to molecular compounds. And I said you're going to notice a trend between ionic and molecular. Here it is. It turns out when we dissolve a molecular compound, and we're just going with sucrose at the moment, right? What do you think is going to happen? Right, so when we have those ionic compounds, remember they turn into ions, polar substance, because one is more positive and one is more negative, right? So here we have all nonmetals, and as they can have oxidation numbers and all that fun stuff, that's not really what we're looking at, right? This is a molecular compound, and molecular compounds do not dissociate into ions because there are no ions in these compounds, right? They're all covalent bonds. The others are ionic bonds, which is why they dissociate. So, to write this process, we would simply write, the same thing on the product side, just dissolved in water. So as I said here, if we drew a little beaker, right, we'd have some Na pluses, and not exactly in those positions, I'm just drawing them randomly, and some Cl minuses floating around, right? That's what it would look like. I could have done that better, but whatever, you can figure it out. And if we drew a little beaker of this, right, we just have little C12H22O11s floating around. Didn't mean to not include the carbon, you know. Stuff like that, right? So it's not going to break into ions. So we can conclude that when dissolved in water, ionic compounds dissociate into ions, and molecular compounds remain the same. Right? So it's going to be the same formula on the product and reactant side. It's just going to be aqueous because there's little smaller particles of that C12H22O11 as opposed to giant crystals. So we're going to come back to this after some acids and bases talk, and I just want to touch on this really quick because we're going to do more of this later in the chapter when we get to titrations and predicting products, but just want to give you a little preview into what we're doing. There are different acid-base theories that are dictated by chemists. Personally, you're going to kind of look at Lewis and Bronsted-Lowry more than you're going to look at Arrhenius, but we go through them just for fun. So this Arrhenius acid-base theory states that acids are compounds that dissolve to produce hydronium or hydrogen cations in solution, and bases are substances that dissolve to produce hydroxide ions in solution. Lewis acid-base theory states that acids are electron pair acceptors while bases are electron pair donors. And Bronsted-Lowry acid-base theory, which for some reason is highlighted in white, I don't know how that happened in this video, but it shouldn't happen in your worksheet. Bronsted-Lowry acids are proton donors, while Bronsted-Lowry bases are proton acceptors. So Arrhenius deals with ions. Lewis deals with electron pairs. And Bronsted-Lowry acid-base theory deals with protons. Right, and an H plus is just a proton, right, because there's no electron. So acids and bases can be split up and categorized into two categories, and those are strong and weak. Okay, strong acids and bases completely dissociate in solution, while weak acids and bases only partially dissociate in solution. What does this mean? And we'll get to the partially dissociating in solution in a second, but if we do just an example of complete dissociation, right? Let's say just we have some pure acid, we're dissolving in water, right? And we end up getting, so it turns out, 2 of the H plus, and 1 of the SO42 minus. So complete dissociation, put it in there, bam, ions, none of the regular molecular species back. So we just have ions. Weak acids and bases partially dissociate in solution, and they're part of what we call a dynamic equilibrium. This means that at any given time, right, the rate at which regular molecular acid molecules are dissociating into ions is happening at the same rate that those ions are coming back together to form molecular acid molecules. Okay, so this is a little difficult to just say, so I'm going to draw this out two ways. Remember in this Iranian acid-base theory, and you're going to hear it at another point as well, hydronium cations, by the way, are H3O plus, right? So if we're dissolved in water and there's an extra hydrogen on the water, right? And we call that the hydronium ion, just to clarify. So I'm going to write this equilibrium state in two different ways. The first way is just going to be as the acid dissociating and coming back. The second is going to be actually adding in the water, so you're going to see where that hydronium ion is coming from. So we have CH3COOH. Just a spoiler alert, this is acetic acid. So acetic acid is vinegar. Vinegar is dilute acetic acid. So fun times. So we have, just remember, our regular species on the reactant side. Let's just say we have some liquid. Right, now this is how I make equilibrium arrows. You can do two full arrows. I like to make the half arrows to remind myself that, you know, the forward and reverse reactions are coming together to make the total reaction, and the rates are the same in this case. So that is equal to, and remember, we're just going to pull off that H, right? And it's at the end this time. Usually acid or acidic protons or hydrogens are written at the front as they're done here. Acetic acid's the one example, or one of the very few examples where it's not done that way, so that's why I wanted to walk you through it, just so you could see that on this, because it's likely to come up on a test. So anyway, the equilibrium comes out to be that acetate anion plus the hydrogen cation. Or you can also write this a different way. And in saying that, I mean that we can actually show adding the water. So we're going to do CH3COOH again. Move this up a little bit first. Right, so now you're going to see where this is coming from. Okay, and so we'll still get that same thing, right? That CH3COO minus. Right, but that proton that comes off, this H, can actually hop onto this oxygen, right? The oxygen will pop one of its lone pairs of electrons off to make room to bond to that hydrogen, in which case we would have plus H3O plus, right? So that's the full expanded example of how you can kind of see this H3O plus species that we're going to talk about. But anyway, just a word to the wise right here. Okay, whether an acid is strong or weak, it does not necessarily dictate whether it is dangerously concentrated, corrosive, carcinogenic, skin irritant, flammable, volatile, you name it. Be mindful of what you're using. Okay, concentrated acetic acid is extraordinarily dangerous, not to mention the smell. I mean, you know what vinegar smells like now. Imagine, you know, at 100% concentration, no dilution. You know, that's really, really powerful. So, yeah, it doesn't limit the danger or toxicity or level of caution that you should be using when working with chemicals in the lab. So make sure you're using caution even if you're working with weak acids. Just because it's partially dissociated doesn't mean it cannot burn you. So now we have to talk about inorganic acid nomenclature. I threw the word acetic acid out there. You're like, how the heck did you get that? I'll tell you. So I say inorganic acid nomenclature. Organic acid nomenclature would be carboxylic acids, and things like that. There are other types as well, but I'll leave you to learn that in organic chemistry. We're just going to stick with this for now. So we're going to talk about two kinds of acids. We're going to talk about binary acids, which just involve protons and a nonmetal anion. And we are going to talk about oxoacids, which actually involve polyatomic anions and protons tacked on to those. So, binary acids just contain, again, a hydrogen and another nonmetal. When dissolved in water, they are named adding this hydro prefix in the front. And this goes in front of the nonmetal name and changing the name on the end of the nonmetal to ic acid. For example, everybody's favorite binary acid, hydrochloric. It's one word. Kind of looks like two words because I want to emphasize hydrochloric acid. Right, this next one, you're going to follow that same thing, hydro prefix. The element is sulfur, ic acid. And acid is separate, so it's not all cumulatively one word. Right? So, with that, I'm actually going to pause the video and have you read and see if you can get these acid names in yourselves. Good luck. I'll be back in a second. So hopefully you attempted to do these following names, and now we're going to go through and see if you were successful. We're definitely starting by talking about nomenclature for this, how we're naming these things called oxoacids. And these are things containing those acidic protons, hydrogens, and polyatomic anions with oxygen in them. Oftentimes, the same nonmetal will form more than one compound, and they'll have a different number of oxygens. When this happens, right? Now, for a general rule, before we even get into composites and different acids of anions, really quickly, I want to just talk about how to name some things just from an anion name. So if you have an anion and it ends in ATE, you're going to chop that off and you're going to add ic. If you have something that ends in ITE, you're going to chop that off and you're going to write OUS on the end. So now you'll see this example, right? This NO3 is nitrate. The NO2 is nitrite. So this would be nitric acid, and this would be nitrous. I'll rewrite that for you. Kind of messy. Acid. Now, sometimes there's more than one of these variations, and my apologies, because these numbers should be subscripted. So it should be HClO4. The 4 should be a subscript on the oxygen, so should the 3 and the 2. So my apologies on that. That is my bad. So there are polyatomic anions of a particular type that halogens also will have, and most commonly have, 4 different variants. So I've shown you the variants with chlorine and oxygen. All these anions have a -1 charge, which is why each of them only has a single hydrogen on them to make it acidic. We're going to do the same thing that we did for the nitrate and nitrite, and we're just going to go through and name these anions and then translate that to acid names. I trust to your care and to your reading this part, but I'm going to talk through it as we do it. So starting at the bottom, we have hypochlorite, then we have chlorite, chlorate, and perchlorate. Right, and those are just the names of the anions, right? So your acid name then, right, would just be, right, perchlor, and then instead of the 8, we're going to add ic, acid. Chlorate, exactly as you think. Chloric, wow, acid. Chlorite, so remember, same root, right? But now we go to OUS, chlorous acid, and hypochlorous acid. Now, really quickly, you'll see the thing that's differentiating the two things that have chlorate is this per. The two things that have chlorite is the hypo. Per means even more, so even more oxygens than chlorate are in perchlorate. Hypo means even less, so there's even less oxygens in hypochlorite than there are in chlorite. That is inorganic acid nomenclature, and base nomenclature is actually much easier because you just name them regularly as ionic compounds and you call it a day. So we're just going to go quick and do these. This one, right here, sodium hydroxide. Right, everyone's favorite. This one right here, lithium hydroxide. So literally just metal hydroxide. Strontium hydroxide. And this last one, nitrogen whoa. Yeah, so don't get too caught up in following a certain pattern. Don't go on autopilot, as a good mentor over at my university says. This is probably the only unique base that you need to know. It is NH3, and if you'd seen this before, you'll know that this is ammonia. Right? Ammonia. NIA. It's not too neat. Let me write that again, but a little more neatly for you. Just so those letters weren't blending together. Everyone knows that ammonia is a base, so you'll learn what kind of base it is in just a second. So now we're going to talk about the difference. What's the whole big deal with strong acids and strong bases? Now, I am going to write the molecular formulas out for these. If you need to write the name, go ahead. But we're now going to go through and say, all right, big moment, which are the strong acids, which are the strong bases? Here come the strong acids. So 3 of your strong acids are binary acids. It so happens that you have your second, third, and fourth halogens in binary form. So HCl, HBr, and HI. So hydrochloric, hydrobromic, hydroiodic acids. And then you also have nitric acid, sulfuric acid. Hold on, let me rewrite nitric acid. Sulfuric acid, hence that example on the strong acids question. And last but not least, perchloric acid. Strong bases. So this is going to be a little bit tedious, but this is just to prove a point. And not really prove a point, but more of just show you the pattern here. Strong bases, ready, set, go. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide. What happened there? And then we also have, and for the sake of writing it down, cesium hydroxide. But I wouldn't really answer that on a test if I said, write 3 strong bases. I wouldn't say cesium hydroxide, just because it's cesium and so reactive. Last ones, we have calcium hydroxide. We have strontium hydroxide. We have barium hydroxide. And for the sake of argument, I'm going to put in a different color magnesium hydroxide. Pretty insoluble. Now, I'm writing that differently. It's pretty insoluble, but when it does dissolve, it does fully dissociate into ions, so it is then a strong base. So if there is an acid that you have, oh, by the way, strong bases are group 1, lower group 2 hydroxides. So if you have an acid that's not one of these 6, a base that's not one of the group 1 or lower group 2 hydroxides, it is a weak acid or weak base, respectively. So just to sum up this video with types of electrolytes, we're just going to identify the strong electrolytes, weak electrolytes, non-electrolytes, right? And what we are going to do is we are just going to make a little flow chart down here. You can write up here, right? You can write stuff up here. I'm just going to make a flow chart because it's a little bit easier for me to do. So it's going to be right here. So we have one area coming off that's non-electrolytes, and the only thing that is a non-electrolyte is a molecular compound. Remember, that's 2 or more nonmetals. We have weak electrolytes. Which can either be weak acids or it can be weak bases. And last but not least, we have strong electrolytes. Which are ionic compounds, strong acids, and strong bases. So that is where we're at, you guys. So this is it, right? I'm going to write this all up here in the summary, in these little lines up here. So strong electrolytes are strong acids, strong bases, ionic compounds. Weak electrolytes are weak acids, weak bases. Non-electrolytes are molecular compounds. That'll do it for this video. Word to the wise about the rest of the Chapter 4 lectures. The other 2 videos are long. Okay, they're about 50 minutes to an hour each. Break those up into chunks, do them in manageable pieces, take your time, really understand that stuff, because that is the bulk of Chapter 4. This stuff really won't be required of you as much as predicting products and titrations, so I would be very mindful about that. But anyway, good luck. Thank you for watching this video, and we'll see you next time.